There are places on Earth where nothing should exist, where temperatures climb past 120 degrees Fahrenheit, where water is more valuable than gold, where the landscape stretches endlessly in every direction, hostile and unforgiving. And yet, in these impossible places, something extraordinary happens. Glass towers rise hundreds of feet into scorching air. Millions of people live, work, and thrive. Gardens bloom. Fountains flow. Entire civilizations emerge from nothing. This is the story of how nations defy nature itself. How engineering, ambition, and human determination turn the most inhospitable places on the planet into thriving metropolises. This is about more than construction. It's about the fundamental question of what's possible when a nation decides that geography is not destiny. Over the next hour, we'll journey across continents and centuries. We'll explore the ancient techniques that first made desert life possible, and the modern technologies that have turned deserts into some of the world's most powerful cities. We'll understand the engineering challenges that make this transformation one of humanity's greatest achievements. Because transforming a desert isn't just about building in a difficult place. It's about creating entire ecosystems where none existed. It's about moving water across hundreds of miles, controlling temperatures that would otherwise be lethal, and solving problems that most engineers will never face. This is how nations transform deserts into cities. To understand the achievement, you first need to understand the obstacle. Deserts are not simply empty spaces. They are active environments that fight against human habitation in ways most people never consider. The average desert receives less than 10 inches of rainfall per year. Some receive virtually none. The Atacama Desert in Chile has regions where no rain has been recorded in modern history. This isn't just inconvenient. It's a fundamental challenge to everything human civilization requires. But the lack of water is only the beginning. Desert temperatures create problems that architects and engineers in temperate climates never encounter. During the day, surfaces can heat to temperatures that would burn skin on contact. At night, that same desert can plunge below freezing. This thermal cycling breaks down materials, cracks concrete, and warps metal. The ground itself presents challenges. Desert soil is often unstable, shifting with wind and water when it does arrive. There's no organic matter to bind it together, no root systems to provide stability. Building foundations in desert sand requires entirely different engineering than building on stable ground. Then there's the wind. Desert winds carry abrasive particles that sandblast everything they touch. They erode buildings, clog machinery, and penetrate every seal and barrier. Modern skyscrapers in Dubai require special glass coatings and constant maintenance to combat this invisible enemy. Yet despite all of this, humans have been living in deserts for thousands of years. And not just surviving, building. The first people to build permanent settlements in deserts understood something crucial. They couldn't fight the desert. They had to work with it. Archaeological evidence suggests that humans began building permanent desert settlements around 10,000 years ago, during the Neolithic period. These weren't just temporary camps. They were planned communities, engineered to survive in one of Earth's harshest environments. The ancient builders of Mesopotamia, the land between the Tigris and Euphrates rivers, pioneered techniques that are still used today. They discovered that thick mud brick walls absorbed heat during the day and released it slowly at night, moderating interior temperatures. They learned that buildings clustered together created shade and reduced exposure to wind. They engineered narrow streets that remained shaded for most of the day. They built underground chambers where temperatures stayed constant year-round. They positioned windows to catch prevailing breezes while excluding the hottest afternoon sun. But the real innovation was water management. These ancient engineers didn't just find water. They moved it. They controlled it. They stored it. The Qanat system, developed in Persia around 3,000 years ago, represents one of humanity's first major hydraulic engineering achievements. These were underground channels, sometimes stretching for dozens of miles, that tapped into groundwater at higher elevations and carried it to settlements through gravity-fed tunnels. Building a Qanat required extraordinary precision. The tunnels had to maintain a constant, gentle slope. Too steep, and the water would erode the channels. Too shallow, and it wouldn't flow. And all of this had to be calculated and constructed underground. using vertical shafts for access. The Cannet system reveals a sophisticated understanding of geology, hydrology, and civil engineering. To build one, engineers first had to locate groundwater. This required knowledge of how water moved through different types of rock and soil, accumulated in certain formations, and could be accessed at sustainable rates. Once they located water, they had to plan the entire route. This meant surveying the landscape, calculating elevation changes, and determining the optimal path. Remember, they were doing this without modern surveying equipment, satellites, or detailed maps. The construction itself was dangerous work. Teams of diggers would excavate vertical shafts down to the water table, sometimes reaching depths of over 100 feet. These shafts were spaced at regular intervals along the planned route, typically every 50 to 100 feet. Then, working in both directions from each shaft, workers would dig horizontal tunnels to connect them. They used oil lamps for light and primitive tools for excavation. They had to maintain the precise slope needed for water flow, while working in confined underground spaces. Some cannets stretched for 30 miles or more. The longest known cannet in Iran runs for over 40 miles, connecting mountain aquifers to distant settlements. These weren't simple ditches. They were precisely engineered systems that had to account for geology, hydrology, and structural integrity. And they worked. Many cannets built thousands of years ago still function today. They transformed desert regions into agricultural centers, supported cities of tens of thousands of people, and enabled civilizations to flourish where none should have been possible. This ancient engineering established a principle that all modern desert cities still follow. If you want to build in the desert, first you must solve water. But water alone doesn't explain why civilizations built in deserts. There's something deeper at work. Something about the desert that calls to human ambition in a unique way. Desert construction is inherently symbolic. Every building, every street, every fountain is a statement. It declares that human ingenuity has conquered impossible odds. It announces power, wealth, and capability in the most visible way possible. Ancient Petra, carved directly into desert cliffs in what is now Jordan, wasn't just practical. It was theater. The Nabateans who built it around 300 BCE understood that creating beauty in a wasteland demonstrated something that building in a fertile valley never could. It showed mastery over nature itself. The same psychology drives modern desert cities. Dubai's Burj Khalifa, the world's tallest building, doesn't exist in the desert by accident. It exists there specifically because it's the desert. Because building the world's tallest structure in one of the world's harshest environments makes a statement that building it in London or New York never could. This isn't new. Throughout history, empires have built their most impressive monuments in their most challenging environments. It's a form of communication, a message to both their own people and to the world. It says, this is what we can do. This is our capability. This is our power. Desert construction also serves a strategic purpose. Historically, desert settlements controlled trade routes. They were positioned at crucial intersections where caravans had to stop for water and supplies. Control the water in the desert, and you control the trade. Control the trade, and you control the wealth. For centuries, Western civilization largely avoided building major cities in deserts. European powers colonized coastlines, river valleys, and temperate regions. Deserts were seen as barriers to cross, not places to settle. Then came the American expansion westward. And with it came a new relationship with the desert. The American Southwest in the mid-1800s presented challenges unlike anything European settlers had encountered. The Sonoran Desert, the Mojave, the Chihuahuan Desert. These were landscapes that defied traditional settlement patterns. Early American settlers in the desert faced the same problems that ancient civilizations had solved thousands of years earlier. But they approached them differently. Instead of adapting to the desert environment, they brought their architectural and engineering traditions with them, and tried to force them to work. The results were often disastrous. Traditional wooden buildings warped and cracked. Conventional wells ran dry. Farms failed. Early desert towns in Arizona and Nevada had extraordinarily high failure rates. Settlements would spring up around a mining claim or water source, grow rapidly, then collapse when resources proved insufficient. But a few settlements survived. And those that did survive began to develop uniquely American approaches to desert construction. They built with local materials, adobe, stone, whatever was available. They adopted some Native American techniques while rejecting others. They experimented with different building orientations, different roof structures, different ventilation systems. More importantly, they began to think about water differently, not as something to find and use carefully, but as something to move, to redirect, to engineer on a massive scale. Las Vegas, Nevada, began as a stopover point on the railroad line connecting Los Angeles to Salt Lake City. In 1905, it was nothing more than a few buildings clustered around a spring. The population was 800 people. There was no reason to believe it would become anything more. Then in 1931, two things happened that would change everything. The state of Nevada legalized gambling, and the federal government began construction on Boulder Dam, later renamed Hoover Dam, just 30 miles away. The dam project brought thousands of workers to the desert. These workers needed housing, food, entertainment. Las Vegas, the nearest settlement of any size, exploded. But more importantly, the dam itself represented something new. The possibility of unlimited water in the desert. Hoover Dam was unlike anything built before. It stood 726 feet tall and contained enough concrete to build a highway from San Francisco to New York. But the concrete wasn't the real achievement. The achievement was controlling the Colorado River. For the first time, a desert region had access to massive, reliable water supplies. The dam created Lake Mead, one of the largest artificial reservoirs in the world. And Las Vegas had rights to draw from it. This changed the calculation of desert construction entirely. Suddenly, the limiting factor wasn't water. It was only imagination and money. If you could afford to pump water and build, you could create anything. Las Vegas began to grow, slowly at first, then explosively. By 1950, the population had reached 25,000. By 1970, it was over 125,000. Today, the Las Vegas metropolitan area is home to over 2 million people, all living in a desert that receives less than 5 inches of rain per year. But building in the desert isn't just about water. It's about heat. And managing heat in desert environments requires engineering that most people never see or think about. The development of modern air conditioning in the early 20th century was as crucial to desert city growth as water engineering. Without it, the modern desert metropolis simply couldn't exist. The human body can't function long-term in sustained temperatures above 95 degrees Fahrenheit. In the summer, Phoenix regularly sees temperatures above 110. Early air conditioning systems were inefficient and expensive. They required massive amounts of electricity and constant maintenance. This made them impractical for widespread use in desert climates, where they would need to run almost constantly for months at a time. The breakthrough came in the 1950s and 60s with improvements in refrigeration technology and electrical grid infrastructure. Suddenly, it became economically feasible to cool buildings year-round. This opened desert regions to mass migration in ways that had never been possible before. Modern desert buildings employ sophisticated cooling strategies. It's not just about running air conditioning. The buildings themselves are designed to minimize heat gain. Glass facades in desert skyscrapers use special coatings that reflect infrared radiation while allowing visible light through. This reduces solar heat gain by up to 70%. The glass itself is often double or triple paned with inert gases between layers for additional insulation. Building orientation matters tremendously. Structures are positioned to minimize western exposure, where afternoon sun is most intense. Walls facing west are often built with extra insulation, or designed without windows entirely. Roofing materials in desert climates are chosen for reflectivity. White or light-colored roofs can reduce cooling costs by 20 to 40% compared to dark surfaces. If Las Vegas represents desert construction for entertainment and tourism, Phoenix represents something different. The transformation of desert into normal, everyday American suburbia. Phoenix's growth is one of the most extraordinary urban expansions in human history. In 1950, the city had a population of 106,000. Today, the Phoenix metropolitan area is home to over 5 million people, making it the 10th largest metro area in the United States. This didn't happen by accident. It happened because of deliberate engineering decisions, water policy, and the application of technology on an unprecedented scale. Phoenix sits in the Sonoran Desert, one of the hottest deserts in North America. Summer temperatures regularly exceed 115 degrees Fahrenheit. Annual rainfall averages just over 8 inches. Yet the city has successfully created a landscape that includes golf courses, swimming pools, and landscaped yards. The key was the Salt River Project, a water management system that began in 1903 with the construction of Roosevelt Dam. This was the first major project of the newly created U.S. Reclamation Service, and it established a model for desert water engineering across the American West. The system captures water from the Salt and Verde rivers, stores it in a series of reservoirs, and distributes it through hundreds of miles of canals. Over time, the system expanded to include 7 dams, 2 diversion dams, and over 1,300 miles of canals. But the Salt River Project wasn't enough for Phoenix's explosive growth. The city also draws water from the Colorado River through the Central Arizona Project, a 336-mile canal system that lifts water over 1,200 feet in elevation and delivers it to central and southern Arizona. This represents engineering on a scale that would have been incomprehensible to earlier generations. The Central Arizona Project alone cost over $4 billion to build and requires massive amounts of energy to operate, pumping water uphill across hundreds of miles of desert. Moving water across deserts isn't just an engineering challenge. It's an economic one. Every gallon of water in Phoenix's swimming pools, every drop watering desert lawns, every flush of every toilet represents energy, infrastructure, and ongoing cost. The Central Arizona Project consumes more electricity than any other single facility in Arizona. Its pumping stations use enough power to supply a city of 150,000 people. This energy cost is passed on to water consumers, but it's also subsidized by state and federal programs. The true cost of desert water is rarely fully reflected in water bills. If Phoenix residents paid the actual cost of moving water hundreds of miles and pumping it thousands of feet uphill, water bills would be several times higher than they are. But there's another hidden cost. The first and oldest approach is groundwater extraction. Beneath many deserts lie aquifers, underground reservoirs of water that accumulated over thousands of years. These can be tapped through wells, providing seemingly abundant water. Phoenix, Arizona largely relied on groundwater through the mid-20th century, and many Middle Eastern cities still do. But there's a critical problem. Aquifers are not infinite. They recharge slowly, over decades or centuries, through rainfall that percolates down through soil and rock. When extraction exceeds recharge, which it almost always does in desert cities, the aquifer depletes. Water tables drop. Wells must be drilled deeper. Eventually, the aquifer becomes economically or technically unfeasible to access. Saudi Arabia learned this lesson painfully. In the 1970s and 80s, flush with oil wealth, the kingdom attempted to become agriculturally self-sufficient by tapping its aquifers for irrigation. For a while, it worked spectacularly. Saudi Arabia even became a wheat exporter. But the aquifers were fossil water, accumulated over millennia. By the 2000s, they were largely depleted, and Saudi agriculture collapsed. This raises questions about sustainability that engineers and policymakers grapple with constantly. Desert cities exist in a state of carefully managed denial about their water situation. They function because of massive infrastructure projects, favorable water rights agreements, and the political will to maintain them. The Colorado River, which supplies water to Phoenix, Las Vegas, Los Angeles, and San Diego, is overallocated. More water has been promised to various users than the river actually contains, even in good years. In drought years, the situation becomes critical. Lake Mead, created by Hoover Dam, has been declining for 2 decades. In 2021, it fell to its lowest level since the lake was filled in the 1930s. This triggered the first ever federal water shortage declaration, forcing cuts in water deliveries. Yet desert cities continue to grow. New subdivisions spread across former desert. New resorts open with elaborate water features. The disconnect between water supply and water demand grows wider. As desert cities mature, architects and engineers are rediscovering principles that ancient builders understood thousands of years ago. The most efficient desert buildings don't fight the environment. They work with it. Modern sustainable desert architecture combines ancient wisdom with contemporary technology. Buildings use thermal mass, thick concrete or stone walls that absorb heat during the day and release it at night, to moderate interior temperatures naturally. This reduces reliance on air conditioning and cuts energy costs. Passive cooling techniques are being revived and refined. Buildings are designed with natural ventilation paths that create airflow without mechanical systems. Courtyards and atriums create shade while allowing light penetration. Window placement is calculated to maximize winter sun exposure while minimizing summer heat gain. Some of the most innovative desert architecture comes from unexpected places. The Bedouin tent, used for thousands of years in Middle Eastern deserts, employs principles that modern engineers are only now fully appreciating. The tent's loose weave allows air circulation while providing shade. Its dark color absorbs heat, but allows it to rise and escape through the top, creating natural convection. Modern interpretations of these principles appear in buildings across desert cities. The Burj Khalifa in Dubai uses a bundled tube structural system that allows for natural ventilation in certain areas, reducing cooling loads. Its Y-shaped floor plan minimizes sun exposure on any given surface. Desert architecture is also increasingly incorporating solar technology. Desert cities have one major advantage: sunshine. Phoenix receives over 300 sunny days per year. Dubai has similar conditions. This makes solar power generation highly efficient. Rooftop solar panels in desert cities can generate far more electricity than the same systems in cloudier climates. Some desert buildings now produce more energy than they consume, becoming net positive contributors to the electrical grid. If Phoenix represents the American approach to desert transformation, suburban sprawl supported by massive water infrastructure, Dubai represents something entirely different. It's a conscious decision to create a global metropolis in one of the world's harshest deserts in less than 3 generations. In 1960, Dubai was a small trading port of about 40,000 people. There was no airport, no port facilities capable of handling large ships, no paved roads beyond the immediate town center. The economy depended on pearl diving, fishing, and small-scale trade. Then oil was discovered, and Dubai's rulers made a decision that would change everything. Rather than simply extract and sell oil, they would use oil wealth to build infrastructure that would outlast the oil itself. The transformation began with basics: roads, electricity, water. But it quickly became more ambitious. Sheikh Rashid bin Saeed Al Maktoum, Dubai's ruler in the 1960s and 70s, had a vision of Dubai as a global trading hub. He ordered the construction of Port Rashid, capable of handling modern container ships. He built Dubai International Airport. He constructed hotels and conference facilities. These weren't just construction projects. They were calculated bets that if you built world-class infrastructure in the desert, business would come. And it did. By the 1990s, Dubai had established itself as a regional center for trade and finance. But the next generation of leaders had even bigger ambitions. If Singapore could be a global city-state, why couldn't Dubai? What followed was construction on a scale never before seen in human history. The Burj Al Arab Hotel, designed to become an icon of luxury. The Palm Jumeirah, an entirely artificial island shaped like a palm tree. The Dubai Marina, a completely new waterfront district built from desert. And then the Burj Khalifa, deliberately designed to be the world's tallest building. Not just tall, the tallest. Building the world's tallest structure requires extraordinary engineering anywhere. Building it in a desert where summer temperatures exceed 120 degrees Fahrenheit and ground conditions are inherently unstable presents challenges that push the limits of materials science and structural engineering. The Burj Khalifa stands 2,717 feet tall, over half a mile high. To put that in perspective, it's more than twice the height of the Empire State Building. It contains enough concrete to build a sidewalk around the Earth's equator. It took 22 million man-hours to complete. But the real engineering marvel is how it stays standing. Desert ground is notoriously unstable, shifting sand, high temperatures that cause expansion and contraction, and the lack of bedrock in many areas. The Burj Khalifa's foundation consists of 192 concrete piles driven over 160 feet deep into the desert sand. These aren't ordinary piles. Each one is reinforced with steel and extends deep enough to reach stable soil layers. Together, they support over 500,000 tons of building weight, plus everything inside it. The building's shape isn't just aesthetic. The Y-shaped floor plan serves multiple engineering purposes. It provides structural stability against wind loads, reduces the amount of glass exposed to direct desert sun at any given time, and allows for natural ventilation in certain areas. Wind loads on a structure this tall are tremendous. At the building's peak, winds can exceed 100 miles per hour. The building sways. It's designed to sway up to several feet in extreme winds. This flexibility prevents structural damage, but it requires sophisticated engineering of the building's core and external support system. The exterior cladding system had to withstand thermal cycling that would destroy conventional materials. During summer days, the building's exterior can heat to over 150 degrees Fahrenheit. At night, it cools rapidly. This expansion and contraction would crack ordinary glass and warp metal. Engineers specified custom-manufactured glass panels with special coatings that reflect heat while maintaining transparency. The aluminum and stainless steel panels are mounted on systems that allow for thermal expansion without creating stress points. Before you can build a city, you must solve a problem that most people never consider. What do you build it on? In temperate regions, this is straightforward. You build on rock, clay, or compact soil that has been stable for millennia. But in deserts, particularly sandy deserts, the ground itself is your enemy. Sand seems solid when you walk on it, but it's not. It's millions of individual grains with no cohesion, no structural integrity. Try to build a heavy structure on sand, and it will simply sink, tilt, or collapse as the sand shifts beneath it. This isn't a minor engineering challenge. It's a fundamental problem that must be solved before any other construction can begin. The first approach is compaction. Engineers use massive machines to compress the sand, forcing the grains together, squeezing out air pockets, creating something approximating solid ground. But this only works to a limited depth and for structures of moderate weight. For skyscrapers, for massive infrastructure projects, for entire urban districts, you need something more robust. That something is deep foundation systems. Instead of resting on the sand, structures are anchored deep below it, into bedrock or at least into stable soil layers. This requires pile driving, literally hammering enormous concrete or steel columns deep into the ground until they reach something solid. In places like Dubai, where skyscrapers exceed half a mile in height, these foundations can extend more than 150 feet below ground. The Burj Khalifa, the world's tallest building, rests on 192 concrete piles, each over 4 feet in diameter, driven deep into the desert floor. The foundation alone required 45,000 cubic meters of concrete, enough to build a small neighborhood of houses. But even this isn't enough in some locations. In areas where groundwater is present, or where sand is particularly unstable, engineers must also deal with liquefaction risk. The possibility that vibration or water saturation could cause the sand to temporarily behave like liquid, catastrophically undermining foundations. This requires sophisticated ground improvement techniques. Injecting cement or other binding agents into the sand, creating underground walls or barriers, even freezing the ground temporarily during construction. Each of these adds enormous cost and complexity to every project. Then there's the challenge of underground utilities. In traditional cities, water pipes, sewer lines, electrical conduits, and communication cables are buried in stable ground where they remain undisturbed for decades. In sandy deserts, these utilities must be carefully protected against sand infiltration and ground movement. A single pipe failure in a desert city doesn't just mean a local repair. It can trigger cascading problems as water erodes surrounding sand, undermining nearby structures. The result is that building in deserts requires far more preliminary engineering than building elsewhere. Before the first building rises, before the first street is paved, months or even years are spent preparing the ground, creating an artificial foundation upon which the artificial city can rest. This also explains why desert cities tend to expand horizontally rather than densely. Every building requires extensive, expensive foundation work. It's often more economical to spread out across cheap desert land than to concentrate development vertically. This creates cities with a distinctive character, vast, sprawling, connected by highways rather than public transit, consuming enormous amounts of land for relatively modest populations. Dubai, for instance, covers over 1,500 square miles, but has a population of just over 3 million. By comparison, New York City packs over 8 million people into just 300 square miles. The difference isn't culture or preference, it's engineering economics. Building on sand makes density expensive, so cities spread outward instead. But this creates its own challenges, as we'll see, because the larger a desert city grows, the more infrastructure it requires, and the more vulnerable it becomes to any disruption in the systems that keep it alive. Keeping the Burj Khalifa comfortable in Dubai's heat requires cooling systems that represent their own engineering achievement. The building consumes as much electricity as a city of 36,000 people. Much of that goes to climate control. The air conditioning system produces the equivalent of 10,000 tons of cooling, roughly the same as melting 10,000 tons of ice every day. The system uses chilled water produced in a central plant at the building's base, then distributed through the structure in massive vertical pipes. But the engineers went further. The building incorporates an ice storage system that produces ice at night when electricity demand and temperatures are lower, then uses that ice for cooling during the hottest parts of the day. This reduces peak electrical load and lowers operating costs. The system also captures condensation from the air conditioning units. In Dubai's climate, this amounts to about 15 million gallons per year. This water is collected, treated, and used for irrigation and cooling tower makeup water. It's a closed-loop system that extracts one resource from the desert air itself. Even the window cleaning system required unique engineering. There are over 24,000 windows. Traditional methods, workers on scaffolding or suspended platforms, would be impossibly dangerous and slow at this height and in this climate. Instead, the building uses a permanent building maintenance unit, essentially a set of sophisticated robotic arms mounted at the building's peak. These machines lower themselves down the building's exterior, cleaning windows and performing inspections. The system can withstand the extreme winds and temperature variations that occur at the building's upper levels. Every system in the Burj Khalifa is redundant. Backup systems have backup systems. This is because failure isn't just inconvenient. At this height, in this climate, system failure could be catastrophic. While the Burj Khalifa represents vertical ambition, Dubai's artificial islands represent horizontal expansion on an almost incomprehensible scale. When you run out of desert, apparently, you create more land from the ocean. The Palm Jumeirah, completed in the mid-2000s, is the world's largest artificial island. It added 35 miles of new coastline to Dubai. The project required moving 94 million cubic meters of sand and 7 million tons of rock. To put those numbers in perspective, 94 million cubic meters of sand is enough to build a wall 3 feet high and 3 feet thick that would circle the Earth's equator. This material was dredged from the seafloor, transported by ship, and carefully positioned to create the palm tree shape that's visible from space. But simply piling sand in the ocean doesn't create stable land. The engineers had to design a system that would withstand waves, currents, and storms while remaining stable enough to support buildings, roads, and utilities. The solution involved creating a protective crescent around the palm structure. This 7-mile-long breakwater was built from massive rocks, some weighing over 6 tons each. The rocks were placed in a specific pattern designed to absorb wave energy, while allowing water circulation. Inside the breakwater, the palm's fronds were created by precisely placing sand in layers. The sand was vibrocompacted, a process that uses vibration to settle and stabilize the material. This creates a foundation strong enough to support multi-story buildings. The entire island was designed with underground utilities, water, sewage, electricity, telecommunications, installed as the island was being built. Streets were constructed with drainage systems sophisticated enough to handle the rare, but intense rainstorms that occasionally hit Dubai. The project employed over 40,000 workers at its peak. It used enough rock to build a wall 6 feet high that would stretch from Dubai to Bahrain. It involved geological surveys, environmental impact studies, and engineering calculations that filled thousands of pages. Dubai's growth created a paradox. As the city expanded, water demand soared. But Dubai sits in a desert where natural freshwater is almost non-existent. The solution? Turn seawater into drinking water on an industrial scale. Dubai's desalination plants produce over 470 million gallons of fresh water every day. This is enough to fill about 700 Olympic-sized swimming pools daily. Desalination works through several processes, but Dubai primarily uses multi-stage flash distillation and reverse osmosis. In multi-stage flash, seawater is heated and passed through chambers at progressively lower pressures. This causes the water to flash into steam, which is then condensed into fresh water. Reverse osmosis forces seawater through special membranes under high pressure. The membranes allow water molecules through but block salt and other minerals. The result is fresh water that meets international drinking water standards. But both processes require enormous amounts of energy. Desalination is one of the most energy-intensive water production methods known. Dubai's desalination plants consume enough electricity to power hundreds of thousands of homes. This creates another paradox. The electricity comes primarily from natural gas power plants. Burning natural gas produces carbon dioxide, contributing to global warming. Global warming increases desert temperatures and reduces what little rainfall these regions receive. The very process that allows desert cities to exist contributes to making the desert even harsher. Dubai is working on solutions. The city is investing heavily in solar power to run desalination plants. It's developing more efficient desalination technologies. But the fundamental challenge remains. Providing water for millions of people in a place where nature provides almost none requires constant, massive energy input. The water produced by desalination is expensive. If residents paid the actual cost, water bills would be prohibitively high for most people. The government subsidizes water costs, but this creates its own problems. Subsidized water leads to overconsumption and waste. When you walk through a desert city, what you see, the buildings, the streets, the landscaping, represents only a fraction of the engineering required to make that city function. Beneath your feet, and hidden from casual view, lies an intricate network of systems without which the city above would cease to exist within hours. This hidden infrastructure is more extensive, more complex, and more critical in desert cities than anywhere else, because nothing about the environment is naturally supportive of urban life. Every function that occurs automatically in other environments must be engineered, maintained, and monitored continuously here. Start with water distribution. In a temperate city, water might come from a nearby reservoir or river, requiring relatively simple treatment and distribution. In a desert city, water might be desalinated from the ocean, requiring energy-intensive processing, then pumped dozens or hundreds of miles to reach users, requiring massive pumping stations and pressure management systems to overcome elevation changes and distance. The pipes themselves must be protected against the heat and sand. Buried water lines can experience temperatures exceeding 100 degrees, which encourages bacterial growth and reduces water quality. This requires either deeper burial, adding cost and complexity, or insulation and active cooling systems. Then there's wastewater management. In most cities, sewage flows to treatment plants largely by gravity through inclined pipes. But desert cities often sprawl across flat terrain with minimal elevation change. This means wastewater must be actively pumped through pressurized systems, requiring pumping stations every few miles and continuous monitoring to prevent backups. Treating that wastewater in desert heat presents its own challenges. Biological treatment processes that work efficiently in moderate temperatures become problematic in extreme heat. This requires either cooling the wastewater, an energy expense, or using different treatment processes designed for high temperatures. Increasingly, desert cities are implementing advanced wastewater recycling. Instead of treating sewage just enough to safely discharge it, they're treating it to standards that allow reuse, for irrigation, industrial processes, even for indirect human consumption after further purification. This makes economic sense in water-scarce environments, but it requires infrastructure far more sophisticated than traditional wastewater systems. Beyond cities and buildings, nations are even attempting to grow food in deserts. This might seem impossible, but it's becoming reality through technologies that would have seemed like science fiction a generation ago. Traditional desert agriculture relied on oasis farming, small plots around natural water sources where crops could grow. Production was limited and communities remained small. Modern desert agriculture aims to do something radically different. Industrial-scale food production in the harshest environments on Earth. Israel has pioneered many modern desert farming techniques. A nation where 60% of the land is desert, Israel had no choice but to innovate. The result has been technologies and methods that are now used worldwide. Drip irrigation, developed in Israel in the 1960s, delivers water directly to plant roots through a network of tubes and emitters. This reduces water waste by up to 70% compared to traditional irrigation. Every drop goes where it's needed, nothing more. But modern desert agriculture goes further. Hydroponics, growing plants in nutrient-rich water solutions without soil, eliminates many challenges of desert farming. Plants grow in controlled environments where temperature, humidity, and light are optimized. Water is recycled continuously, reducing consumption to a fraction of traditional farming. Vertical farming takes this even further. By stacking growing layers vertically, farms can produce multiple times more food per square foot than traditional agriculture. In a desert where land isn't the limiting factor but water is, this efficiency matters enormously. Dubai has invested in some of the world's largest vertical farms. These facilities, housed in climate-controlled warehouses, produce millions of pounds of fresh vegetables annually using 95% less water than conventional farming. The United Arab Emirates has set ambitious goals to produce 70% of its food domestically by 2040. This might seem impossible for a desert nation, but with these technologies, it's becoming achievable. If Dubai represents what's possible in desert construction today, Saudi Arabia's NEOM project represents the future. Or at least, it represents one vision of it. NEOM is a planned megacity in the northwestern desert of Saudi Arabia. But calling it a city doesn't capture the scope. The project area covers 10,000 square miles, larger than the state of Massachusetts. The estimated cost is $500 billion, though some analysts suggest the final cost could exceed $1 trillion. At the center of NEOM is the line, a linear city that challenges every assumption about urban planning. Instead of spreading outward from a center, the line is a continuous structure 105 miles long, 200 meters wide, and 500 meters tall. The concept is radical. All 9 million residents would live within this single, continuous building. The structure would be entirely walkable. No resident would be more than 5 minutes from any essential service. High-speed rail running through the center would connect the entire length in 20 minutes. The line would be powered entirely by renewable energy. Solar panels would cover the roof. Wind turbines would supplement power generation. The structure itself would be oriented to minimize solar heat gain while maximizing natural light. But the engineering challenges are staggering. Building a continuous structure 105 miles long in the desert would require solving problems that have never been solved before. The foundation alone would need to adapt to varying geology across the entire length. The structural system would need to withstand thermal expansion and contraction on a scale never before attempted. Water would come from desalination plants on the Red Sea coast, then distributed throughout the structure. Waste management, power distribution, and climate control would all need to function across this unprecedented distance. Critics question whether the line is even possible. The engineering challenges might be insurmountable. The costs might prove too high. The vision might be too ambitious. But that's what people said about building cities in the desert in the first place. While Middle Eastern nations have captured global attention for desert construction, China has been quietly building some of the world's largest desert cities with far less fanfare. Urumqi, the capital of Xinjiang province, sits in the heart of Central Asia, surrounded by some of the world's most extreme deserts. With a population of over 4 million, it's one of the world's most remote major cities. It's farther from an ocean than any other large city on Earth. But Urumqi is just one example. China has been systematically developing its western deserts for decades, building cities, infrastructure, and industrial facilities in regions that were virtually uninhabited a generation ago. The approach differs from Western and Middle Eastern desert development. Chinese desert cities often emerge as planned developments, built to serve specific strategic or economic purposes. They're designed to support resource extraction, manufacturing, or regional administration. Water management in Chinese desert cities employs technologies similar to those used elsewhere: long-distance water transfer, desalination where applicable, and sophisticated distribution networks. But the scale is uniquely Chinese. The South-to-North Water Transfer Project, while not exclusively serving desert regions, is the world's largest water transfer project. It moves water over 1,400 miles from the Yangtze River Basin to northern China's arid regions. The project's 3 routes have a combined capacity to transfer over 44 billion cubic meters of water annually. This is water engineering on a scale that dwarfs anything attempted in the United States or Middle East. It's the equivalent of moving the entire annual flow of the Colorado River twice over. Chinese desert cities also employ extensive greening programs. Massive tree planting initiatives aim to create green barriers against desertification and sandstorms. Some cities have planted millions of trees in surrounding deserts, attempting to literally change the local climate. Building in deserts requires materials that can withstand conditions that would destroy conventional construction. The materials science that makes modern desert cities possible is sophisticated, constantly evolving, and rarely appreciated by those who live in these cities. Concrete in desert environments faces unique challenges. Traditional concrete can crack and spall when exposed to the extreme temperature cycling of desert climates. During the day, surfaces heat rapidly. At night, they cool just as fast. This causes expansion and contraction that creates stress in the material. Desert concrete formulations include special additives that improve thermal stability. Fly ash and silica fume create denser concrete that resists thermal cycling. Special aggregates with low thermal expansion coefficients reduce the stress caused by temperature changes. Some desert projects use concrete made with desert sand as part of the aggregate. This was long considered impossible. Desert sand grains are too smooth and round to bond properly in concrete. But new technologies and chemical additives have made it feasible, reducing the need to import crushed stone from distant quarries. But this is just the beginning of the materials challenge. Building a city requires materials: steel, concrete, glass, copper, aluminum, and countless others. In most locations, at least some of these can be sourced locally. There might be stone quarries, clay deposits, forests for timber, or at least manufacturing facilities within reasonable transportation distance. In deserts, none of this exists. The desert provides only sand, and while sand is technically useful for concrete production, desert sand is actually problematic for construction. Its grains are too smooth and rounded from wind erosion, unlike the rough, angular sand from riverbeds that bonds properly in concrete. This means that even the most abundant material in the desert can't be used for the city's most fundamental building material. Everything must be imported: steel from distant mills, concrete aggregate from quarries hundreds of miles away, glass from specialized manufacturers, copper for electrical systems, aluminum for windows, timber for forms and finishing, all transported across vast distances at enormous cost. Glass technology for desert buildings has advanced dramatically. Modern desert glass can reject up to 70% of solar heat while remaining transparent. This is achieved through multiple technologies: low emissivity coatings, selective spectral filtering, and multiple panes with inert gas fills. Some desert buildings use electrochromic glass that can change its tinting electronically. During the hottest parts of the day, the glass darkens, reducing solar heat gain. As temperatures moderate, it lightens, allowing more natural light while maintaining thermal efficiency. But materials must not only be transported, they must be suitable for desert conditions. The extreme heat, temperature cycling, sun exposure, and abrasive sand create demands that materials don't face elsewhere. Concrete, for instance, cures differently in desert heat. If it dries too quickly, it becomes weak and prone to cracking. This means desert construction often happens at night, when temperatures are cooler, or requires continuous water spraying to keep concrete moist during curing. a water expense that wouldn't exist in temperate climates. Steel expands and contracts dramatically with temperature changes. A steel beam that's 100 feet long will expand by nearly an inch when heated from 70 to 120 degrees. Bridges, building frames, and infrastructure must all be designed with expansion joints and flexible connections to accommodate this movement. Glass must be treated to reflect heat and UV radiation. Otherwise, building interiors would become ovens regardless of air conditioning. This specialized glass is more expensive than standard glass, adding to construction costs. Even paint and sealants must be desert-rated. Standard formulations can fail within months under intense UV exposure and thermal cycling. This means higher material costs and more frequent maintenance. Metal components in desert construction must resist not just heat, but also the abrasive effects of windborne sand and the corrosive effects of salt in coastal desert areas. Specialized coatings and alloys resist these conditions better than conventional materials. Even paint and sealants require special formulations. Standard paint can fade, crack, and fail within months in intense desert sun. Desert-grade paints include UV stabilizers and reflective pigments that maintain color and integrity for years. Every desert city faces the same fundamental challenge. They consume enormous amounts of energy simply to exist. Climate control, water production, and basic operations require power on a scale that would seem excessive anywhere else. This creates both a problem and an opportunity. The problem is that energy consumption in desert cities can be 2 to 3 times higher per capita than in temperate climates. The opportunity is that deserts receive more solar energy than almost any other environment on Earth. Solar power in deserts can achieve efficiency levels impossible elsewhere. Clear skies, intense sunlight, and low humidity all contribute to optimal solar panel performance. A solar installation in the Mojave Desert can generate 50% more electricity than an identical installation in Germany. Desert cities are increasingly leveraging this advantage. Dubai has built some of the world's largest solar farms, with plans to generate 75% of its electricity from clean sources by 2050. The Mohammed bin Rashid Al Maktoum Solar Park, when complete, will generate 5,000 megawatts, enough to power hundreds of thousands of homes. Saudi Arabia is investing heavily in solar power as part of its Vision 2030 plan. The kingdom aims to generate 58.7 gigawatts from renewable sources by 2030, with solar power comprising the majority. Phoenix and Las Vegas are also expanding solar capacity rapidly. Arizona's abundant sunshine makes it one of the most attractive locations for solar development in the United States. But solar power creates new engineering challenges. Solar panels must withstand extreme heat. Surface temperatures can exceed 180 degrees Fahrenheit. This reduces panel efficiency and can damage components. Modern panels use heat-resistant materials and cooling systems to maintain performance. Dust is another major issue. In desert environments, dust and sand can accumulate on panels, reducing output by 20 to 40%. Large solar installations employ automated cleaning systems that use minimal water to keep panels clean. Energy storage is also critical. Solar power only works when the sun shines, but desert cities need power at night. Battery systems, thermal storage, and other technologies are essential for maintaining 24-hour power supply. Roads, railways, and airports in desert cities face engineering challenges that most people never consider. Asphalt and concrete behave differently at extreme temperatures, and conventional designs often fail. Asphalt in desert heat becomes soft and pliable. This leads to rutting, permanent deformations in the road surface caused by vehicle weight. In extreme cases, asphalt can actually flow, creating dangerous surface conditions. Desert highways use specially formulated asphalt mixes with modified binders that remain stable at higher temperatures. These mixes can cost 20 to 30% more than standard asphalt, but they last significantly longer and require less maintenance. Concrete highways in deserts face different problems. Temperature changes cause expansion and contraction. Without proper design, this creates joint failures and cracking. Modern desert highways use sophisticated joint systems with special expansion materials that accommodate thermal movement. Airport runways in desert cities require even more specialized engineering. aircraft place enormous concentrated loads on pavement. When that pavement is heated to 150 degrees Fahrenheit or more, conventional designs fail rapidly. Dubai International Airport, one of the world's busiest, uses concrete runways designed specifically for extreme heat. The concrete is thicker than standard specifications, uses special aggregates, and incorporates cooling systems that circulate water beneath the surface during the hottest periods. Railways face their own challenges. Steel rails expand in heat. A mile of rail can expand several inches on a hot day. Without proper engineering, this expansion can cause rails to buckle, creating catastrophic derailment risks. Desert railways use continuously welded rail, with sophisticated stress management systems. The rails are installed at specific temperatures and held in tension to prevent buckling. Track geometry is monitored constantly, and maintenance crews make adjustments as needed. Even the ballast, the crushed rock that supports railroad tracks, requires special consideration in deserts. Desert ballast must resist wind erosion while providing drainage during rare but intense rainstorms. Electrical infrastructure in desert cities must handle extreme loads. Air conditioning creates enormous peak demand during hot afternoons, precisely when electricity is most needed everywhere in the region simultaneously. This can cause grid strain that leads to brownouts or blackouts if not carefully managed. Desert cities typically address this through massive overcapacity, building far more generating capacity than they'd normally need, just to handle those peak hours. Dubai's electricity system, for instance, has a capacity roughly 50% higher than its average demand, a margin that would be considered wasteful elsewhere, but is necessary here. They're also investing heavily in grid storage, batteries and other systems that can store electricity during low demand periods and release it during peaks. This allows more efficient use of generation capacity and provides backup during outages. Communication infrastructure faces unique challenges as well. Sand and dust can interfere with wireless signals, requiring denser networks of antennas and repeaters than would be needed elsewhere. Underground fiber optic cables must be protected against sand infiltration and temperature extremes that can degrade signal quality. Then there's cooling infrastructure beyond individual air conditioning units. Some desert cities are building district cooling systems, centralized plants that produce chilled water distributed through pipes to buildings across an area. This is more efficient than having every building run its own air conditioning, and it allows better integration with power systems and waste heat recovery. Dubai has one of the world's largest district cooling networks, with over 1.2 million tons of cooling capacity, enough to air condition roughly 100,000 average American homes simultaneously. All of this infrastructure must be monitored constantly. Desert cities employ sophisticated sensor networks that track water pressure, temperature, flow rates, electrical loads, air quality, and countless other parameters in real time. Control centers monitor this data 24/7, ready to respond to any anomaly that might indicate a problem. This is necessary because failures cascade quickly in desert environments. A water main break isn't just an inconvenience. It can erode sand around underground utilities, damaging electrical and communication lines. A power outage doesn't just mean lights go out. It means air conditioning stops, which can make buildings uninhabitable within hours. The cost of maintaining all this infrastructure is substantial. Desert cities typically spend 2 to 3 times more per capita on infrastructure maintenance than temperate cities, and they must replace components more frequently due to accelerated wear from heat, sand, and constant use. But this hidden infrastructure is what makes desert cities possible. The shimmering towers and green parks and comfortable interiors exist only because beneath and behind them lies an intricate machine that never stops working, that requires continuous attention and resources, and that represents perhaps the greatest engineering challenge in urban development today. Behind every desert megaproject are workers who labor in conditions that push human endurance to its limits. The human cost of building in the desert is rarely discussed, but it's substantial. Construction in desert heat is dangerous. When temperatures exceed 110 degrees Fahrenheit, the human body struggles to cool itself effectively. Heat exhaustion and heat stroke become serious risks. Workers can become dangerously dehydrated within hours. Modern desert construction projects implement strict safety protocols. Work often stops during the hottest parts of the day. Workers are required to take frequent breaks in air-conditioned facilities. Water is constantly available. Medical staff are on site to treat heat-related illness. But these protections aren't universal. Reports from major desert construction projects have documented instances of inadequate worker protection, particularly among migrant labor forces. Some workers face pressure to continue working in dangerous heat. Others lack adequate access to water or medical care. The physical toll goes beyond heat. Fine desert sand can cause respiratory problems with long-term exposure. The reflective glare of desert sun can damage eyes. The extreme UV radiation at desert construction sites causes skin damage and increases cancer risk. There's also the psychological dimension. Building in the desert often means working far from home and family. Construction camps in remote desert areas can house thousands of workers in Spartan conditions. The isolation, combined with harsh working conditions, takes a mental health toll that's difficult to quantify. As desert construction has matured, conditions have generally improved. Better regulation, increased awareness, and pressure from international organizations have pushed many projects toward higher labor standards. But challenges remain, particularly in regions where labor protection laws are weak or poorly enforced. The transformation of deserts into cities represents human achievement, but it's important to remember the humans who make it possible, often under extraordinarily difficult conditions. Desert cities exist in a peculiar relationship with climate change. On one hand, they're already adapted to extreme heat and water scarcity. On the other hand, they're among the most vulnerable to the intensifying conditions that climate change brings. Global temperatures are rising, but desert regions are warming faster than the global average. Some desert areas have seen temperature increases of 3 to 4 degrees Fahrenheit over the past several decades. This might not sound dramatic, but when baseline temperatures already exceed 110 degrees, every additional degree matters. Higher temperatures mean higher cooling loads. Air conditioning systems must work harder and longer to maintain comfortable indoor conditions. This increases energy consumption, which in turn generates more greenhouse gases, creating a feedback loop. Water availability is also changing. Many desert regions depend on snowmelt from distant mountains for their water supply. As global temperatures rise, snowpack is decreasing. Some models project that the Colorado River's flow could decrease by 10 to 30% by mid-century. For cities like Phoenix and Las Vegas, this would be catastrophic. Desert cities are responding in various ways. Dubai is investing heavily in renewable energy to reduce its carbon footprint. Phoenix is implementing water conservation programs and exploring alternative sources. Saudi Arabia is developing technologies to reduce the energy cost of desalination. But there's a fundamental question. Can desert cities remain viable as conditions become more extreme? At what point does the engineering solution become too expensive or too energy-intensive to sustain? Some researchers suggest desert cities might actually become more attractive as other regions become uninhabitable due to heat and humidity. The dry heat of deserts, while extreme, is more survivable than the wet bulb temperatures that could make tropical regions literally uninhabitable. But this creates an ethical dilemma. Should we be investing in making deserts habitable? Or should we be investing in making currently habitable regions more resilient? Is desert urbanization a solution to climate migration, or a distraction from addressing the root causes of climate change? These questions don't have easy answers, but they're becoming increasingly urgent as more nations look to their deserts as frontiers for expansion. Building and maintaining a city in the desert is extraordinarily expensive, far more so than equivalent development in temperate regions. This raises a fundamental economic question. Why do it? What economic logic justifies the enormous additional costs of desert urbanization? The answer varies by location and historical context, but it generally involves one of several economic drivers that make the additional costs worthwhile. For the Gulf states, the answer is straightforward: oil and natural gas. The Persian Gulf region contains roughly 30% of the world's proven oil reserves and 20% of natural gas reserves. These resources provide wealth that dwarfs the cost of building desert cities. Saudi Arabia, the UAE, Qatar, and Kuwait have oil revenues measured in hundreds of billions of dollars annually. For these nations, building cities in the desert isn't a choice. The oil is where it is, and extracting it requires infrastructure, which requires cities to house workers and their families. The question isn't whether to build in the desert, but how extensively. Moreover, oil wealth has allowed these nations to pursue economic diversification strategies that require urban infrastructure. Dubai has deliberately transformed itself into a global financial, trade, and tourism hub. This requires the infrastructure of a world-class city: airports, ports, hotels, office buildings, telecommunications, regardless of location. The economic logic is to use temporary resource wealth to build permanent infrastructure that can sustain the economy after oil revenues eventually decline. Whether this strategy will succeed remains uncertain, but it explains the massive construction boom across the Gulf region. In the American Southwest, the economic logic is different. Cities like Phoenix, Las Vegas, and Albuquerque grew primarily because of lifestyle amenities rather than natural resources. The desert offered space, sunshine, and lower costs than crowded coastal cities. After air conditioning made desert living comfortable, these cities attracted retirees seeking warm, dry climates, businesses seeking lower costs and taxes, and workers seeking affordable housing. The population growth created its own economic momentum. More people meant more services needed, more jobs created, more businesses established. Las Vegas represents a unique case. A city built almost entirely on entertainment and tourism. The desert location is almost irrelevant to its economic function. The city could theoretically be anywhere. But once established, the existing infrastructure and brand recognition make relocation impossible. The city's economy generates enough revenue to justify the costs of maintaining desert infrastructure. Phoenix represents a more typical pattern. It started as a small agricultural and mining support town, grew as air conditioning made it livable, and then expanded rapidly as businesses and retirees relocated from more expensive regions. Today, it's one of America's fastest-growing metropolitan areas, with an economy based on technology, healthcare, education, and manufacturing. The economic sustainability of these cities depends on continued population growth and economic activity. As long as people and businesses continue moving to them, the tax base expands, revenues increase, and infrastructure costs can be absorbed. But this creates a kind of Ponzi scheme dynamic. The cities must keep growing to remain economically viable. If growth slows or reverses, the fixed costs of maintaining desert infrastructure become burdensome relative to the tax base. Water infrastructure sized for 2 million people doesn't cost much less to maintain if the population drops to 1 million. But the revenue available to maintain it drops by half. This vulnerability became apparent during the 2008 financial crisis. Las Vegas, Phoenix, and other desert cities were hit particularly hard. Property values collapsed, construction halted, unemployment soared, and tax revenues plummeted. The cities didn't fail, but they experienced severe stress that revealed how dependent they were on continuous growth. 4 newer, more ambitious desert cities being planned today, such as Saudi Arabia's NEOM project, a proposed $500 billion city in the desert. The economic logic is more speculative. These are betting on creating economies where none currently exist, attracting global investment, businesses, and residents through sheer ambition and infrastructure quality. NEOM, for instance, proposes building a city of 1 million people in the Saudi desert, powered entirely by renewable energy, with advanced technology integrated into every aspect of urban life. The economic case rests on the idea that the combination of ambitious vision, massive investment, and strategic location can create a hub that attracts global talent and capital. Whether such projects will succeed is unknown. They represent a fundamentally different approach than cities that grew organically over time. They're attempting to manufacture economic ecosystems through sheer force of will and capital deployment. This reveals a broader truth about desert city economics. They're never self-sustaining in the way that cities in fertile, well-watered regions can be. They always require continuous input of capital, whether from natural resource extraction, migration of wealth from elsewhere, or external investment. This doesn't necessarily make them economically irrational. Many economic activities are worth pursuing even if they require ongoing subsidy. But it does mean that desert cities are fundamentally more fragile economically than their temperate counterparts. They exist because someone, governments, investors, populations, has decided the benefits justify the costs. The moment that calculation changes, the economic foundation weakens. The question isn't whether desert cities can be economically viable. Clearly they can't given sufficient resources. The question is whether they can remain economically attractive over the long term, through changing economic conditions, environmental challenges, and competition from alternatives. That question remains open, and the answer may differ for each city depending on its specific circumstances and economic foundation. Desert cities exist in defiance of nature, but they cannot escape the environmental consequences of that defiance. The resource consumption, waste generation, and ecological disruption inherent in transforming desert into city create environmental challenges that are becoming increasingly difficult to ignore. Start with energy consumption. Desert cities use vastly more energy per capita than temperate cities, primarily for cooling and water desalination. Dubai's per capita energy consumption is roughly double that of New York City. This energy must come from somewhere, and currently, it comes primarily from fossil fuels. The Gulf states burn enormous quantities of natural gas and oil to power their cities. Saudi Arabia consumes roughly a quarter of its oil production domestically, most of it for electricity generation and desalination. This represents oil that could otherwise be exported for revenue, creating an opportunity cost in addition to environmental impact. The carbon emissions from this energy consumption are substantial. The UAE has one of the highest per capita carbon footprints in the world, exceeding even the United States. Qatar and Kuwait are similarly high. This creates both climate change contributions and reputational challenges as global pressure to reduce emissions intensifies. The irony is that deserts are actually ideal for renewable energy generation. Solar radiation in deserts is among the highest on Earth. Wind resources can be substantial. Space for solar farms or wind turbines is abundant and cheap. Several desert regions are beginning to leverage this advantage. Morocco's Noor Ouarzazate solar complex is one of the world's largest concentrated solar plants, capable of generating electricity even after sunset using thermal storage. The UAE is investing heavily in solar energy, aiming to generate 44% of its electricity from renewables by 2050. California's Mojave Desert hosts numerous solar farms collectively generating thousands of megawatts. Nevada, Arizona, and New Mexico are similarly developing solar resources. But transitioning desert cities to renewable energy faces challenges beyond just building generation capacity. Solar power is intermittent. It produces nothing at night, precisely when many desert cities experience peak cooling demand as buildings release the day's accumulated heat. This requires either storage solutions, batteries, pumped hydro, thermal storage, or maintaining fossil fuel backup capacity. Water consumption presents another environmental challenge. Desalination doesn't just consume energy, it produces brine waste that's typically discharged back into the ocean. This concentrated salt water can create dead zones in marine environments, particularly in enclosed water bodies like the Persian Gulf where circulation is limited. Research on the Gulf's marine environment shows declining biodiversity and ecological health in areas near desalination plants. The combination of hot brine discharge and the chemical additives used in desalination processes creates conditions that many marine species cannot tolerate. Some newer desalination facilities are experimenting with brine management strategies, diluting it before discharge, using it for salt production, or disposing of it in deep ocean currents. But these add cost and complexity to an already expensive process. Desert cities also disrupt natural desert ecosystems in ways that are less visible, but ecologically significant. Deserts aren't lifeless wastelands. They're complex ecosystems with species adapted to extreme conditions. Many of these species are endemic, existing nowhere else on Earth. Urban development destroys habitat, fragments ecosystems, and introduces invasive species that outcompete native organisms. The groundwater extraction that supports some desert cities lowers water tables, killing deep-rooted desert plants and eliminating springs and seeps that serve as critical water sources for wildlife. Light pollution from desert cities affects nocturnal species, many of which are specifically adapted to navigate by starlight. The heat island effect alters local microclimates for miles around cities. These impacts might seem minor compared to deforestation or coral reef destruction, but desert ecosystems are often fragile and recover slowly. A plant that takes 50 years to mature can be destroyed in minutes of construction. Species driven extinct by urban expansion are gone permanently. There's also the question of waste. Desert cities generate enormous amounts of waste, construction debris, household garbage, industrial byproducts, and have limited options for disposal. In temperate regions, landfills can be located in marginal land with minimal environmental impact. In deserts, there is no marginal land. It's all marginal from a human perspective, but it's all habitat from an ecological perspective. Some waste streams are particularly problematic. Air conditioning systems use refrigerants that are potent greenhouse gases if they leak. The massive construction activity uses concrete, which has a huge carbon footprint. Landscape irrigation with recycled wastewater introduces pharmaceuticals, microplastics, and other contaminants into desert soil and groundwater. Desert cities are beginning to address these issues, driven partly by genuine environmental concern, and partly by recognition that resource efficiency makes economic sense. Abu Dhabi's Masdar City project aims to be carbon neutral and zero waste, using renewable energy, extensive recycling, and sustainable urban design. Phoenix is investing in water recycling to reduce pressure on Colorado River supplies. Las Vegas has implemented strict water conservation measures, reducing per capita consumption by 30% over the past 2 decades despite population growth. But these efforts, while significant, don't fundamentally change the equation. A desert city, however efficient, still consumes vastly more resources per capita than most temperate cities. It still requires continuous input of water, energy, and materials. It still generates waste and emissions. The environmental reality of desert cities is that they exist in a state of continuous emergency. They're dependent on life support systems that must never fail, that consume resources at rates that cannot be sustained indefinitely, and that create environmental impacts that compound over time. This doesn't necessarily mean they're unsustainable. Sustainability is a complex calculation involving technology, economics, and social priorities. But it does mean that desert cities face environmental challenges that will require continuous innovation, investment, and adaptation to address. The question is whether the benefits they provide, economic opportunity, cultural development, strategic presence, justify the environmental costs they impose. That's ultimately a social and political question, not just an environmental one. Cities aren't just physical infrastructure. They're social organisms, complex webs of human relationships, cultural traditions, and community bonds. In cities that evolved organically over centuries, these social structures develop naturally, layer upon layer of accumulated history and shared experience. In desert cities, particularly those built rapidly in recent decades, this social fabric must be manufactured as deliberately as the physical infrastructure. This creates unique challenges and opportunities that shape these cities' character in profound ways. The Gulf cities exemplify this dynamic most clearly. Dubai's population is roughly 90% expatriate. People from India, Pakistan, Philippines, Western nations, and dozens of other countries, all drawn by economic opportunity. The native Emirati population is a small minority in their own country. This creates a city of temporary residents. Most expatriates don't intend to stay permanently. They're there to work, save money, and eventually return home or move elsewhere. This transience means people invest less in community building, maintain connections to their countries of origin, and view the city primarily as an economic opportunity rather than a home. The result is a society that can feel atomized, lacking the deep community bonds that form in more stable populations. Neighborhoods don't develop the same character they would if residents expected to live there for generations. Social institutions, clubs, religious communities, civic organizations, tend to be more formal and less organic than in traditional cities. Labor is highly stratified by nationality and income. Construction workers from South Asia live in labor camps separate from the city proper, often in difficult conditions. Middle-income office workers live in apartment complexes. Wealthy expatriates and Emiratis live in villas and high-end developments. These groups inhabit the same city, but exist in largely separate social worlds. This stratification is reinforced by legal structures that make permanent residency and citizenship extremely difficult for expatriates to obtain. Most work on temporary visas tied to specific employers, creating power imbalances where workers have limited ability to change jobs or negotiate conditions without risking deportation. These social dynamics create cities that can feel artificial, lacking the organic messiness of cities that grew naturally. Streets are clean and orderly. Crime is low. Infrastructure works efficiently. But there's also a sense of sterility, of life lived in parallel tracks that rarely intersect meaningfully. American desert cities have different social dynamics, but face their own challenges in building community. Phoenix, Las Vegas, and other southwestern cities have grown so rapidly that they lack the accumulated social capital of older cities. Most residents are transplants from elsewhere, bringing diverse cultural backgrounds and expectations. This can create vitality and innovation, new ideas, fresh perspectives, lack of entrenched interests resisting change. But it can also create rootlessness, a sense that the city lacks identity beyond its economic function. Las Vegas struggles with this particularly acutely. As a city built on entertainment and tourism, it can feel like a permanent stage set, a place where everyone is performing rather than living authentically. The transient nature of much of its population, both tourists and workers in the hospitality industry, makes stable community building difficult. Phoenix has worked deliberately to create cultural institutions and community identity. Museums, performing arts centers, sports teams, universities, all serve to give the city character beyond just economic function. But these institutions are relatively new, lacking the depth that comes with generations of accumulated tradition. The environmental extremity of desert cities also shapes social life in distinctive ways. The necessity of spending most time in climate-controlled interior spaces rather than outdoors changes how people interact. In temperate cities, street life, parks, and public spaces facilitate casual interaction and community building. In desert cities, particularly in summer, this outdoor social life is largely absent. This drives people toward privatized social spaces, shopping malls, members-only clubs, private compounds, that are comfortable but create barriers to the kind of casual social mixing that builds community cohesion. There's also an interesting pattern where desert cities attract specific demographic groups: retirees seeking warm, dry climates, workers in specific industries, hospitality, construction, technology, seeking opportunities, people attracted to frontier environments where social constraints might be looser than in established regions. This self-selection can create dynamic, but also unstable populations. Cities become younger or older than average. They might have fewer families with children or more. They might attract risk-takers and entrepreneurs, or people fleeing problems elsewhere. These demographic peculiarities shape everything from politics to consumption patterns to social services needed. Desert cities must also navigate tensions between preservation of traditional cultures and embrace of global modernity. The Gulf states are attempting to maintain Islamic traditions and Arab cultural identity, while building cities that are globally connected and culturally diverse. This creates complex negotiations over dress codes, alcohol policies, gender relations, and religious practices. These tensions aren't unique to desert cities, but the rapidity of change intensifies them. When a society transforms from traditional to ultramodern within a single generation, the cultural dislocations can be profound. The social fabric of desert cities reveals a broader truth. You can engineer physical infrastructure relatively quickly, but social infrastructure, trust, community, shared identity, institutional depth, develops much more slowly. Desert cities are still young. Whether they'll develop the rich social character of older cities, or whether their manufactured nature will always create a certain artificiality, remains to be seen. What's clear is that building a successful city requires more than just physical infrastructure. It requires creating conditions where people can build lives, not just make livings, where they can form communities, not just networks, where they can feel at home, not just comfortable. This is the frontier that desert cities are still exploring. The desert cities of today are impressive, but they represent just the beginning of what's possible. Technology is advancing, understanding is deepening, and new approaches are emerging that could transform how we build in deserts. The next generation of desert cities won't just fight the desert. They'll work with it, leveraging its unique characteristics rather than purely opposing them. Water technology is evolving rapidly. Next-generation desalination uses graphene filters that require far less energy than current reverse osmosis systems. Forward osmosis systems use natural osmotic pressure gradients to reduce energy consumption further. These technologies are still experimental, but they promise to make desalination dramatically cheaper and more sustainable. Atmospheric water generation, extracting moisture from air, is improving as well. While the desert air is dry, it still contains some moisture, and specialized systems can condense that moisture into usable water. Currently, this is expensive and energy-intensive, but improving technology and integration with renewable energy could make it viable for supplementing water supplies. More sophisticated water recycling is also emerging. Advanced treatment processes can purify wastewater to standards exceeding natural freshwater, making it suitable for any use including drinking. Singapore already recycles virtually all its wastewater through its NEOM program. Desert cities are beginning to adopt similar approaches, viewing wastewater not as waste but as a resource to be captured and reused indefinitely. Energy systems are advancing toward what some call energy autonomy, cities that generate all their own power from renewable sources. The combination of solar energy, battery storage, and smart grid management makes this increasingly feasible for desert cities. Saudi Arabia's NEOM project aims to be powered entirely by renewable energy. The combination of solar farms, wind turbines, and potentially green hydrogen production could create a city with no carbon emissions from energy production. Battery technology is improving rapidly. Lithium-ion batteries are being supplemented by new chemistries, sodium-ion, solid-state flow batteries, that offer different advantages in cost, energy density, and lifespan. As storage becomes cheaper and more capable, the intermittency of solar power becomes less problematic. Building design is also evolving. Architects are developing structures specifically optimized for desert conditions rather than simply adapting temperate designs. This includes passive cooling through thermal mass and natural ventilation, building orientation to minimize sun exposure, and materials that reflect heat rather than absorbing it. Some experimental buildings use phase-change materials in walls that absorb heat during the day and release it at night, reducing cooling requirements. Others incorporate wind towers, traditional Middle Eastern architecture that channels breezes through buildings for natural cooling, with modern controls and materials. Urban planning is becoming more sophisticated about managing heat. Green corridors with drought-tolerant plants provide shade and evaporative cooling. Light-colored surfaces reduce heat absorption. Street orientation and building heights are optimized to create shade during the hottest hours. Food production technology is advancing beyond current hydroponic systems. Cellular agriculture, growing meat directly from cells without raising animals, could allow protein production in deserts without the water and land requirements of traditional livestock. Vertical farming efficiency continues improving, potentially allowing cities to produce significant food locally despite the harsh environment. Some researchers are exploring even more radical approaches. Atmospheric processors that extract carbon dioxide and use it as feedstock for producing food through chemical processes. Algae cultivation systems that thrive in high heat and produce both food and biofuel. These technologies are speculative, but they suggest possibilities beyond current approaches. Transportation is evolving as well. Electric vehicles are particularly well suited to desert cities. They don't overheat like combustion engines, and the abundant solar energy can power them sustainably. Autonomous vehicles could make car sharing more efficient, reducing the number of vehicles needed. Some cities are experimenting with personal rapid transit, small automated vehicles running on dedicated guideways, as an alternative to both cars and traditional mass transit. These systems could be more practical in sprawling desert cities than conventional subways or light rail. Perhaps most importantly, our understanding of sustainability is maturing. Early desert cities focused purely on resource consumption, getting enough water, generating enough power, maintaining acceptable temperatures. Next-generation approaches focus on efficiency, recycling, and integration. The concept is circular urban metabolism. Cities that minimize waste by ensuring that the output of one process becomes the input for another. Wastewater from homes becomes irrigation water for parks. Waste heat from power generation helps with desalination. Organic waste is converted to biogas or fertilizer. This systems-level thinking could make desert cities far more sustainable than current designs. Instead of linear resource flows, import, use, discard, they'd create closed loops where materials and energy are continuously recycled within the urban system. There's also growing interest in smaller, more distributed desert settlements rather than massive megacities. The logic is that smaller settlements are more manageable, less vulnerable to catastrophic failure, and can be more carefully integrated with the local environment. These wouldn't be isolated outposts but networked communities connected by transportation and communication infrastructure, sharing resources and specializing in different economic functions. This model could provide the benefits of urban living without the vulnerabilities of concentrating millions of people in harsh environments. Climate change adds urgency to desert city innovation. As global temperatures rise, more regions will experience desert-like conditions. Techniques developed in current desert cities could become applicable to regions that weren't previously considered deserts. Conversely, desert cities are developing resilience strategies to handle even more extreme conditions than they face today. If temperatures rise another 5 or 10 degrees, current approaches may no longer suffice. Planning is beginning now for these possibilities. The future of desert cities isn't just about building more of them. It's about building them better, smarter, more sustainably, and more resiliently. The engineering challenges that seemed nearly insurmountable decades ago are being solved. The question now is whether we can solve them in ways that are environmentally responsible, socially inclusive, and economically sustainable over the long term. The desert cities of the future might look very different from those of today, but they'll still represent the same fundamental human ambition: to inhabit the inhospitable, to thrive where nature says we shouldn't, to prove that ingenuity can overcome even the harshest environments. We began by asking what it takes to build a city where nothing should exist. Now, having explored the engineering, the economics, the environmental costs, and the human dimensions of this endeavor, we can understand that the question itself was incomplete. Desert cities aren't just about what it takes to build them. They're about why we build them. They're expressions of something fundamental to human nature. The drive to push boundaries, to prove ourselves, to demonstrate that we're not limited by the circumstances we inherit. Every desert city makes a statement. Las Vegas announces that human desire for entertainment can sustain a metropolis in one of North America's driest regions. Phoenix declares that the American dream of space and sunshine can triumph over heat and aridity. Dubai proclaims that ambition and wealth can create a global city anywhere, regardless of natural limitations. These aren't merely practical achievements. They're philosophical statements about humanity's relationship with nature. Are we part of the natural world, bound by its constraints? Or are we separate from it, able to reshape it according to our will? Desert cities answer: we can be both. We're constrained by nature, the laws of thermodynamics, the water cycle, the limits of materials and energy. But within those constraints, human ingenuity has enormous freedom to create, to innovate, to build environments that defy what seems natural or possible. Some researchers suggest desert cities might actually become more attractive as other regions become uninhabitable due to heat and humidity. The dry heat of deserts, while extreme, is more survivable than the wet bulb temperatures that could make tropical regions literally uninhabitable. But this creates an ethical dilemma. Should we be investing in making deserts habitable? Or should we be investing in making currently habitable regions more resilient? Is desert urbanization a solution to climate migration, or a distraction from addressing the root causes of climate change? These questions don't have easy answers, but they're becoming increasingly urgent as more nations look to their deserts as frontiers for expansion. The engineering required to make deserts habitable has driven innovations that benefit humanity far beyond the desert itself. Desalination technology developed for Gulf cities now provides water for coastal regions worldwide. Solar energy systems optimized for desert conditions are being deployed globally. Water recycling techniques pioneered in water-scarce environments are helping cities everywhere become more sustainable. But desert cities also serve as warnings. They show us what happens when growth becomes an end in itself, when we build without fully considering long-term consequences, when we assume that technology will always solve the problems created by previous technologies. They reveal the fragility of complex systems. A desert city isn't just vulnerable to catastrophic failures. It's vulnerable to the gradual erosion of the resources and conditions that make it possible. Declining water sources, rising energy costs, climate change, economic shifts. Any of these could make a thriving desert city suddenly unviable. Yet despite these vulnerabilities, desert cities continue growing. More are being planned. Billions of dollars are being invested in making deserts habitable. This tells us something important. The human drive to build, to expand, to prove ourselves capable of ambitious endeavors is powerful enough to overcome reasonable caution about sustainability and long-term viability. Perhaps that's appropriate. Civilizations have always pushed into marginal environments, and some succeeded while others failed. We learn from both outcomes. The cities that thrive show us what works. The cities that struggle or fail teach us what to avoid. Desert cities are laboratories where we test the limits of human capability. Can we build sustainably in harsh environments? Can we create communities in places that require continuous engineering just to remain habitable? Can we maintain civilization in locations where nature actively opposes our presence? We don't know the answers yet. Some desert cities are barely a generation old. Their ultimate success or failure will only be clear decades or centuries from now. What we can say is this: building cities in deserts represents one of humanity's most audacious engineering challenges. It requires marshaling resources on a massive scale, coordinating expertise across countless disciplines, and maintaining vigilance over systems that must never fail. It demands both humility, recognizing that we're working against nature, not with it, and confidence, believing that human ingenuity can overcome even the harshest constraints. And it reveals something essential about who we are as a species. We're not content to inhabit only the comfortable places. We push into the difficult ones. We take on challenges that seem impossible. We build where we shouldn't, simply to prove that we can. The desert cities rising across the world today, from the Persian Gulf to the American Southwest, from North Africa to Australia, are more than just collections of buildings and infrastructure. They're monuments to human ambition, testaments to engineering capability, and experiments in sustainable habitation that will shape how humanity adapts to an increasingly challenging environmental future. The desert will always be hostile to human life, but it will also always be a canvas upon which civilizations prove themselves. And as long as humans retain the ambition to build, to grow, to demonstrate their capabilities, there will be cities rising from sand, monuments to ingenuity standing in defiance of the elements. That story, of transformation, of defiance, of human will reshaping the inhospitable, is still being written. The desert cities of today are just the latest chapter in a narrative that stretches back to ancient Mesopotamia, and will continue as long as civilization endures. The question isn't whether we can build cities in deserts. We've answered that decisively. The question is whether we should, and having done so, whether we can maintain them sustainably and responsibly for generations to come. That question remains open, its answer still unfolding across the shimmering horizons of the world's great deserts.